So, good morning, everyone. So, let's just quickly get started with today's problems. So, basically, what the series is going to be is me solving the beginners sheet from GfG. So basically, we'll just be going through each of these problems, and then I'll be trying to solve them, and maybe I can even explain these approaches to each of these problems, so you can code along and solve them too. Um, Obviously, there will be maybe better approaches to solve these problems as well, and these are not the only approaches to solving them, but this may give you a start. So quickly, let's just get into the problem sheet itself so we can begin solving it. So we are going to the first problem now, which says search an element in an array. So whenever you're trying to solve a problem, so first we read the question and try to understand what exactly it's asking. So basically, the first question tells us, given an integer array and another integer element, the task is to find if the given element is present in the array or not, right? So this basically seems like a search problem. So where we really have to go through each element of the array and check if the element that we are seeking is present in the array. So what our task is, the task is to complete the function search, which takes the array and its size n and the element x as inputs and returns the index of the first occurrence of x in the given array. If the element x does not exist in the array, the function should return -1. So how do we solve this using Python? I think the basic approach would be to use something like for loop. So for I comma val in enumerate ARR, that means, so I'm just going through each element inside the array itself. So what this enumerate function does is something special. So it does not only allow you to iterate through each element of the array, it also returns the index. So for example, here, if I had an array like 1, 2, 3, so the values will be what's stored in val will be 1, 2, and 3. But what's stored in I in every iteration will be 0, 1, and 2. That means the index of these elements, right? So what I'll basically just do here is for first, I just have to change my coding language. Sorry about that. For I comma val in enumerate ARR if val is equal to x, return I, else we just go and return -1. So let's just compile this code and run it. Yes, so let's submit it as well. Okay, so there's also other ways to solve this exact same problem using Python, which is basically using a library function. So try return arr.index of x, then except return -1. So basically, what this index function returns is it returns the index of the element that we're looking for inside the array. And if this element x is not inside the array, it basically throws an exception. So that's what we're doing here. So first, we're actually asking the library function, if you're able to find the index of x in the array, return it. If you can't and you're throwing an exception, I'll return -1 back to the user. So let's just run this as well. Okay. So these are just two approaches to solve this problem, and feel free to use the one that you like. I like the first approach more because it makes more sense and it scales to every other language as well. So let's just look at, and just one more thing, if I would also suggest be well versed with library functions that each language offers, because that they can make your whole coding experience easily, much easier than what it is. Because a lot of times, especially in real life, uh, the algorithm itself is not the trick, and if you can find an easier library function to do it, always use the library function. One thing is because it's very, very optimized, and the second thing is your code becomes very manageable because instead of writing a sort algorithm or something like that, you're just calling a library function that does the sorting for you. So let's just quickly go to the next problem. So basically, what the next problem we'll take up will be finding the minimum and maximum element in an array. So given an array A of size n of integers, your task is to find the minimum and maximum elements in the array. So there is a very, very easy Python way to finish this problem. So what we simply say is return min of A and max of A. So let's just see what this compiles to. Yeah. So basically, what this min and max functions do is that you supply a list to these min and max functions, and basically, what min does is returns the minimum value inside the list, and max does something very similar. It returns the maximum value inside the list. But this solution probably does not scale to other languages, so let's write a solution that scales to other languages as well. So first, what I'll do is min is equal to a of 0 and max is equal to a of 0. So first, I'm just basically telling, assume that the minimum value and the maximum value are the zeroth element in both these arrays. So for I in range 1 comma n. So what I'm saying is here is basically if you have an array like this 1 3 1 4 2 5. So basically first I'm assuming both the maximum and the minimum in the array is the first element, and then I'll look through all the other elements in the array, right, or list. If any element in the array is less than the current minimum, then I'll make that the new minimum. If any element in the array is greater than the current maximum, I'll make that the new maximum. So there are again ways, many ways to do that. So where we just take a very, very simple approach here. If a of I is less than min, the new minimum is equal to a of I. If a of j less than max, mean greater than a of I greater than max, max is equal to a of I. Now all we have to do is return min and max, right? So let's just sum this as well. Perfect. So now that we have solved our two problems, let's quickly just go on to the third problem. So the third problem that we'll be tackling today is missing number in an array, right? So again, our approach whenever we find a problem is first to actually read the question properly and understand what it's trying to ask. So given an array of size n minus 1 such that it contains only distinct integers in the range of 1 to n, find the missing element. Okay, perfect question, right? So basically, what it's saying is, let's say they give an n value like 4, right? So what are the numbers from 1 to 4? 1, 2, 3, and 4, right? So there's what they're basically saying is, in their input, one of these numbers is missing, either 1, 2, 3, or 4, right? Our task is given the value of n and given a list where one of these numbers is missing, right? Our task is to find which number is missing, right? So how do we solve this? One very, very simple approach is basically just finding out, okay, if ideally if I had all these numbers, what would be the sum? Okay, let's say if I had n is equal to 4, right? So the sum of all these elements would be 1, 2, 1 plus 2 plus 3 plus 4. So that is 3, 3, 4. That is 10, right? Now, in my missing list, right, if I add all these numbers up, 1 plus 3 plus 2, I would be getting something like 6. Now, I think you've already spotted where the trick is. Now, if I simply subtract this value of the new sum from the old sum, what I'll have is the value of the missing number, right? And even if, let's say, instead of 2, I had 4 here, right? So what is 1 plus 3 plus 4? So 4 plus 4 is 8, right? So this is equal to 8. Now, if I say 10 minus 8, then I'll get the value 2, which is the missing number. So this is the basic logic behind this program, right? So let's just quickly code out this solution also. Sum is equal to n into n plus 1 by 2 for val in array sum minus equal to val. And now so what I'm basically saying is first You find out the whole sum from the ideal situation. And as you encounter numbers in this list with a missing number, keep subtracting. For example, if I encounter 1, I subtract um, 10 minus 1, so I get 9. Then I encounter 3, so I subtract 3 from 9, I get 6. Then I encounter 2, so finally I get 4. So this is the missing value. So that is what's happening here. So let me just write that as well. So whatever is remaining at the end of all these subtractions should be my missing number, right? So let's just submit this as well. Perfect. So now let's just move on to the third problem. That is the wave, fourth problem, sorry for today, which is the wave problem, right? So, okay, so let's just again, our trick remains the same. Whenever we encounter a new problem, we basically look at the problem, try understand what it's talking about, what should we actually output, right? So they're saying, given a sorted array ARR of distinct integers, sort the array into a wave-like array in place. In other words, arrange the elements into a sequence such that array of 1 is greater than equal to array of 2, less than equal to array of 3, greater than equal to array of 4, less than equal to array of 5. If there are multiple solutions, find the lexicographically smallest one. The given array is sorted in ascending order, and you don't need to return anything to make changes in the original array itself. So okay, so this problem statement may have been quite confusing. So let's just look at this is another approach. Whenever we're not able to understand the problem statement itself, we always look at the inputs and output examples given. So we're able to actually make sense of what they're asking, right? So basically the array looks like this. So 1, 2, 3, 4, 5, and the output they're asking is for 2, 1, 4, 3, 5. Okay, so let me just try drawing this, right? Why they may call it a wave array, right? So now how do waves look? So they look something like this, right? Yeah. Now, if you look at this example, right? So 1, 2, 3, 4, 5 has got converted into 2, 1, 4, 3, 5. So let me just place these numbers on the wave. So 2, 1, 4, 3, and 5, right? So if you look at any number on the crest, right? So 2, it is greater than its adjacent element 1. Okay, and if you look at any element in the trough or like at the bottom, it's smaller than the two nearby elements. So 2 and 4 are greater than 1. And it's the same case for 3. So 3 is smaller than 4 and 5, and 4 is greater than 1 and 3. And this is how the whole wave array concept works. Okay, but if you realize the problem itself is quite simple, right? So if you just look at the inputs and outputs, it says 1, 2, 3, 4, 5, and we have to give 2, 1, 4, 3, 5. So if you look at this, right, it's just swapping the two nearby adjacent elements. So 1 and 2 get swapped to give us 2 and 1. 3 and 4 get swapped to give us 4 and 3. And finally, 5 remains as is because it doesn't have anything to swap with, right? So how would I go about coding this is for I in range 0, comma. So here we have 0, 1, 2, 3, 4. We have five elements, right? So if because I have an odd number of elements, if you think about it, I won't be able to swap the last number, right? Because 5 doesn't have any pair. But if there were even numbers, I would be able to swap 5 also, right? If I had 1, 2, 3, 4, 5, 6. So what I do is if I have an odd number of elements, so if I say n if n mod by 2 else n minus 1. Okay, so basically what I'm saying here is at each step, right, start with the index 0, okay, and increase by 2. So basically this is what a 0 and the 2 at the end mean. But now if you have, suppose you have, so here it'll be n mod by 2 equal 0. Okay, so yeah, if there are an even number of elements in the array, consider the whole array itself, but I mean whole list itself. Else, if there are an odd number of elements, leave out the last index, right? Let it be by itself because you can't find a swap partner for it. So that's what basically this piece of the code means. N if n mod by 2 equal to 0, or else n minus 1. So if there are odd elements, we just decrease the n count. Or if there are even elements, we just keep it as is because we'll find pairs for every number. So basically, all I have to do here is ARR of I, comma ARR of I plus 1 is equal to ARR of I plus 1, ARR of I. So, do I have to return anything? The task is complete, convert to, okay, and I think you don't need to return anything. Yeah, sure. So let's just see the result of this code as well. Hmm, ARR is not defined because this is called A. So let's run it again. Yeah, perfect. So this problem is solved as well, right? Now let's just look at some other types of problems. We'll be skipping a few of these. So the basic goal is for us to understand a diverse range of problems rather than just sticking to one approach. So let's just solve this problem, anagram, right? So let's look at the problem itself. Given two strings A and B consisting of lowercase characters, the task is to check whether the two strings are anagrams of each other or not. An anagram of a string is another string that contains the same characters, only the order of characters can be different. For example, act and tag are anagram of each other. If the strings are anagrams, return true or else return false. Geeks for geeks, BZ. Okay, so if you see here, right, geeks for geeks can be created by just substituting these letters in string B in the correct positions, right? So you can say geek for and then geeks. So geeks for geeks. So it's equal to string A. And so that's why these two things are anagrams. So they have the exact same characters, but only their orders are different. Okay, and if you see allergy and allergic, yeah, they are not anagrams. Okay, so you don't need to read input or print anything. Your task is to complete the function is anagram, which takes string A and B as input parameter and checks if the two strings are anagrams of each other. The function returns true if the strings are anagrams, else it returns false. Right. So for two strings to be anagrams of each other, the basic condition would be that they have to be formed of the same number of characters, right? So let's just simply just code that in first. If len A is not equal to len B, return false. Okay. So now one approach that we usually take with string problems, and once they have to do with some processing some sort of characters in the string, is basically to create like some sort of occurrence or frequency array that tells how many times each character in the string has occurred, right? So for example, if I have a string like AAA and I have, so basically what I do is I have a list of 26 variables, right? So from 0 to index 25. So let me just call it frequency list so it makes more sense to us, right? So here this will be the frequency of A, here will be the frequency of B, here will be the frequency of C, so on and so forth until the 25th index, that is Z, right? So when I have something like AAA and I want to convert it to this frequency list that tells me how many times each like characters occurred inside the string. So basically what output I'll be getting here is something like 300 and zeros all the way up to Z, right? So this is basically what a frequency list would give us. Now, how do I convert any string into a frequency list? This would probably be very simpler in the other languages where you just have to subtract an integer value from a character and then you finally get that character to index the array itself. But in Python, when you're handling the characters, it's quite different. So first, let me just create a list, frequency list. So OCC is equal to 0 into 26. So this is our base case, right? So we have this list of 26 spaces where it's telling no character has occurred at all. So it's the base case. So for CH in A, so that means for each character in A, do this, right? So OCC of odd of CH minus odd of A plus equal to 1. So what do we think this is doing is quite simple. Okay, so the odd value basically returns some sort of Unicode integer representation of the character itself. For example, the odd value of 90, A is 97 and B is 98 and so on and so forth, right? So for example, now if you look at our occurrence list or the frequency list, so it's basically this sort of list that has these indexes from 0, 1, 2, 3, 4, and so on and so forth. And each index represents how many times the character at that index has appeared. For example, 0 stands for how many times the character A has appeared. B stands for how, I mean, 1 stands for how many times character B has appeared. 3 stands for how many times character C has appeared, so on and so forth, right? So now when I say odd of CH minus odd of A, for example, if I had the string BA, right? So basically for CH and A, that means for every character in A, do the following processing. So first it goes to this letter B. So what is the odd value of B? That is 98, right? So 98 minus odd value of character A is 97. So 98 minus 97, we'll get 1. So we just increase whatever values in that position by 1. So if you remember at the initial stage, everything was 0. So we just increase this by 1 and so on and so forth. We go processing this list. Okay. So now once we have converted whatever was there in A into a frequency list, so we'll do the same thing for B, but we'll do something a bit different, right? So now what I want to do is I'll just get the index of odd CH minus odd B, right? So now I have an index value that says, okay, for this character inside my string B. So this ID will point at the character of whose frequency that I want to access, right? So if suppose if I have the character A in the string, sorry, this will not be odd B, sorry, this will be odd A itself. So if I want to access the index value of, let's say, the character C in the string B, right? So odd value of C would be something like 99. So 99 minus 97 would give us 2. So if you know, if you remember in our occurrence frequency list, what basically the index to represent, how many times C occurred in the array A, right? So now if um, OCC of ID equal to 0, okay, return false. Should we, okay, either true or false, that's what we're trying to return, else OCC of ID minus equal to 1. So basically, what are we trying to do here, right? So let me say I have two strings A, B, and this is my string A, and this is my string B. Okay, so at the end of the first step, when we convert everything to a frequency array, so basically we'll have something like OCC is equal to 300 and so on and so forth, right? So now for each character in B, we do the following process. So we just take the one character in string B, then we get the index value. So index value of A will be odd A minus A, that is 0. So now if I still have those many characters in my previous string to form this string, so what I basically do is, okay, this is fine. So I just subtract it by 1, right? So again, when I come here, I again subtract it by 1. I can form two A's from the previous string, but once I reach B, you'll notice a problem here, right? I have to, in order to form the string B, I need this letter B, right? But if you look at my string A, I didn't have any occurrence of B itself. So it'll be impossible for me to create the string B. So at that time, basically what I do is if I'm not able to find any characters in the occurrence list to make the new string, I just return false. Else, I just subtract it by 1 continuously. Now, if I never encounter a failed case, so if I'm able to make all the characters in string B using the characters in string A, so I just have to return true because then they become anagrams of each other. So that is how this problem is solved. Okay, let's just submit this as well. Perfect. So now we have solved, with that, we have solved five problems for today. So let's just quickly go into the next problem, which will be our mm, transpose problem, transpose of a matrix, right? So now quickly, we saw at the start of the day, we saw some array-based problems and we saw a string-based problem. And one thing that I would like to tell you at this stage is always remember the frequency list concept, because that's a recurring pattern in almost many of the string problems. So that will be your key weapon in tackling many of the string problems, right? So let's look at this problem, transpose of a matrix. So whenever we're talking about matrix in other languages, we can call it a multidimensional list. So it's usually a matrix is like a 2D list, right? So it has a certain number of rows and a certain number of columns, and you're supposed to process that sort of a data structure, right? So write a program to find the transpose of a square matrix n into n. Transpose of a matrix is obtained by changing the rows to columns and columns to rows. Okay, so perfect. So basically, I think many of you who have taken math courses before would really know what transpose of a matrix is. But if you don't, no problem. So basically, what they're saying is the key lies here: changing rows to columns and columns to rows. So if you have like 1 1 1 1 and 2 2 2 2 3 3 3 3 4 4 4 4, so just write the first row as the first column. So it'll be 1 1 1 1. Then write the second row as the second column, 2 2 2 2. Then write the third column as the third row as the third column, and write the fourth row as a fourth column. So this is basically how you would get a transpose of a matrix, right? Okay, so there's also another way to look at the same problem. Okay, let's just consider this diagonal, the principal diagonal, right? So 1, 2, 3, 4. Let's just consider this diagonal. And if you look at the original matrix and the transpose of this matrix, you can just say that in the transpose of the matrix, the elements are mirrored over the principal diagonal. Okay, so what do I mean by that? Mirrored over the principal diagonal, right? So if you see, if I just consider this 1, 2, 3, 4 like as a mirror that stands like diagonally like this, in the original 2D matrix, we had 2 here and we had 1 here, right? But in the transpose matrix, these two positions got shifted around it. So we have 1 here and 2 here. We had 2 here and 1 here, and now they just got flipped. 1 here and 2 here. Now if I look again, if I had 1 here and 3 here, right? I mean, I had 3 here and 1 here. Now if I flip it over this principal diagonal, I'll get 3 here and 1 here. That's what we have in the answer, 3 and 1. So this is basically how you can think about a transpose of a matrix to be found, right? So let's just quickly code out the solution for this too. For I in range n. So do this sort of processing for all the rows. Okay. So first what I'll do is for j, I'll just write the code for us to understand a bit better. Okay. So matrix of I j, matrix of j I is equal to matrix of j I, matrix of I j. Okay, so this basically, if you look at this statement, right, this is how you swap to numbers in Python, right? So basically, you say it's something like the general form is like a comma b is equal to b comma a. So the value of b gets put into a, and the value of a gets put into b. So this is how you would essentially swap characters in Python. I know in other languages you might have to take a more comprehensive approach. So first assign the value of a into a temporary variable, then uh, make the value of a into b, and then finally convert whatever was stored in the temporary variable, put it back in b, right? So this is how you would swap variables in other languages, but this statement is how you usually swap variables in Python. I mean, of course, you can do it this way too in Python, but it's much easier to do it the way that's just shown here. Okay. So let's just look at the logic of the program. For So I'm basically saying for I in range n. So that means for every row, do the following process. For j in range I, so for the zeroth row, I won't have to iterate through any element inside the row itself, right? So because I value will be zero, and so there will be absolutely no iterations here. And the logic is very simple. In the first row, right, uh, you see there is no element that I have to flip over the principal diagonal, right? So that is the basic logic here. But so the second row, I'll only have to flip this element over the principal diagonal. So only this two. So 2 and 1 will get flipped. In the third row, I'll have to flip these two, 3 and this 3. And the fourth row, I'll have to flip this 4, and this 4. So that is basically the whole logic here. Okay, so now let's just look at what we have to return. You don't need to read input or print anything. Complete the function transpose. This that is you need to. Okay, in place. So because it's in place, so this should be fine. So let's just submit this. Perfect. So we have solved this problem too. So basically, just remember for the transpose is basically like flipping over a principal diagonal. So we go through each row and we check how many elements inside this row we have to flip over the principal diagonal. So for the zeroth row, we don't have to flip anything over the principal diagonal. For the first row, yes, we have to flip one element and so on and so forth. So that's why for I in range n, that means for do it for each row. For j in range I, that means for those many elements that are needed to flip in that row, perform the following process, and then just swap these two. So matrix of ij comma matrix of ji becomes matrix of ji and matrix of ij. So just to confirm, so the index of this element in the 2D matrix is basically 1 comma 0, and the index of this element is 0 comma 1, right? So that is what we are flipping. So we are flipping 1 comma 0 with 0 comma 1. And if you have an element here like uh, so the index of this would basically 2 comma 0. You will have to flip this with what element? The element at 0 comma 2. So I'll flip it with this element. So 3 and 1 get swapped. And you see here also, so this 3 which was here went here, and the one that was here came here. So that is basically how the whole transposition works, right? So now that we have solved that problem too, we'll go to our next problem. That is okay, we'll just take up a very, very simple problem for now, just to take a bit of a break. It says check whether the kth bit is set or not, right? So, what does this mean? Given a number n and a bit number k, check if the kth index bit of n is set or not. A bit is called 1, or a bit is called set if it is 1. Position of the set bit 1 should be indexed starting with 0 from LSB in binary representation of a number. Index is starting from 0. You don't need to return true or false. Driver code will take care of printing yes and no. Okay, so again, this the question itself may have seemed a bit confusing, but our strategy remains the same. If the question is seems very confusing to us, the first thing that we do is read the question once again, if you can. But if you're still not able to understand the question, we just look at the inputs and the outputs. Okay, so let's just look at the input, right? So the input n is equal to 4 and k is equal to 0. Okay. So what they're saying is the binary representation of 4 is 100, right? So let's just write that down. So 4 is equal to 100 and k is equal to 0, right? Okay. So basically what they're saying is the kth bit from this direction, right? So least significant bit in binary will go from right to left, right? So this is the least significant bit. So what they're basically saying is uh, K is giving the index of the bit I have to find out if it's set or not, right? So this will be index 2, this will be 1, this will be 0. Okay, right. So in my question, what is the index of, uh, is the 0th index bit a set bit or not, right? So let's just look at our input. So for 4, the binary representation is 100. And when k is equal to 0, so in this index, we have the value 0. Is it a set bit or no? Or no? No, right? Because 0 is not set bit, 1 is actually a set bit. And because we have a 0 here, we have to return no. Okay. So let's just look at the return as well. Okay, it returns either true or false. So if the a bit at index 0 is 0, we just return false. Okay. Now, what if the value k was equal to 2, right? If I look at the index 2 here in my input that says 100, so the index 2 is a set bit 1, right? In this case, I'll have to return true, right? So this is all that is there to the problem, right? So how can I solve this, right? Let me just for clarity's sake, let me go back to that example, right? And talk about some cases, right? So k is equal to 0. When k is equal to 0, it's quite simple, right? In the binary representation, when k is equal to 0, that means I always check the element at the least significant bit, right? You can take any even number, for example, 8 is equal to 10000. 6 is equal to 0110. So if you take any even number, you'll always notice that the last bit would be 0, right? Can this be a good solution provider for us to solve the problem? Absolutely, right? So if k is equal to 0 and the number is even, it's very obvious, right? So it's not a set bit. But now, what if they give me another value of k is equal to 1, right? So how do I find, um, for example, for the number 6, how do I find what will be the bit value of this number at the index 1, right? Why? Let's just try dividing this 6 by 2 and see what happens, right? So if I divide 6 by 2, I'm going to get 3, right? So the binary representation of 3 is 0, 1, 1, right? If you notice here, right, whenever I divide by a number by 2, I'm basically, what I'm doing is I'm just removing the least significant bit out of the equation, right? If I divide 6 by 2, I'm getting 3. So the binary representation becomes 0, 1, 1, right? So this is what was here. Now can I say, if I have to find the index 1, bit at index 1, I just have to divide it once by 2, right? And now if I have to find the bit at index 2, I just have to divide this once more, right? So this becomes integer division. So this becomes 1. So basically, now for k is equal to, I just have to access the last bit, right? So now we are going to use these two logics that we had before. If a number is even, that means the least significant bit will not be a set bit. If it's odd, it'll be a set bit. If it's even, the least significant bit will not be a set bit. Okay. And when we have a higher value of k, we just keep repeatedly dividing it by 2 until we reach the value of k is equal to 0. And when we reach the value of k is equal to 0, whatever is there in the last least significant bit position, that will be the value that we have to return true. Or if it's 1, we return true. If it's 0, we return false. So let's just code out this solution also. While k is greater than 0, k n by y equal to 2. So basically in Python, when you're using double slashes, that means integral division. If you just use n by is equal to 2, or that means n is equal to n divided by 2, that will give a float answer, right? So this, in this case, we don't want a float answer, we want an integer answer. So basically it rounds down to the lowest number. So if I have 5 divided by 2, um, 5 by 2 will give me 2.5, but 5 slash slash 2 will give me 2, because it just takes out the decimal part and only returns the integer part, right? So that's what n by y equal to 2 would do. And then k minus equal to 1. So return true. When do we return true? If the number is odd, because whenever a number is odd, the bit at the least significant bit will be a set bit, right? So if n mod by 2 equal to 1, else return false. Okay, so let's just run this as well. Perfect. Right. So now we have solved this problem too. Again, the basic approach is very simple here. We just have to remember two things. Whenever a number is even, the least significant bit will be 0. Whenever a number is odd, the least significant bit will be 1. And when we have to find a higher uh, bit position within the binary representation, all we have to do is keep dividing that number by 2 until we reach the required value of k, until we make k 0. And when k becomes 0, then we know based on the least significant bit, we tell if the kth bit was a set bit or not. Simple approach, right? So now that we have solved that problem also, now let's quickly move into another data structure which is quite essential in a lot of use cases, and it's I'd say like understanding this data structure would like really help you understand even trees and graphs and things like that, right? So let's just start with a very simple problem on this data structure. So node at a given index in a linked list. Okay, so what essentially is a linked list, right? So let me just remove all of this data and let me paint what a linked list might look like. So basically in arrays you would have, I mean in other languages arrays are immutable, but in Python we have lists which are you can add elements, you can do a whole lot of operations on them, right? So okay, let's just take an example of an array, right? So basically what an array is like this homogeneous collection of elements of the same data type, right? So you have something like one, two, three, four. And in arrays, you basically have like this index value associated with each element, right? So when I say a of 0, that means I'm basically telling it to get the element at the zeroth index. The element at the zeroth index is 1 here, element at the first index is 2, so on and so forth, right? But in many scenarios, we don't really want an array which has like a fixed size, right? So, for example, let's say you start out with a small school, right, and you have like maybe like 200 students at the start, and so you create an array of 200 to store the roll numbers of each of these students, right? But what happens if the next year the students in your school becomes 1,000, right? Then do you recreate all of this and say, okay, I'm going to delete that array and I'm going to create a new array for all these roll numbers. I'm going to make it 1,000. And maybe what is the next year? It's 1,500. Then you have to increase it again. And what if suddenly it falls back to 400, the number of students in your campus for whatever reason? So then you have to change it. So many times you want to change uh, the number of elements inside a data structure. And arrays don't allow you to do that. You always have to assign a huge chunk to them and then change things around with them. So that is not very efficient. So that's why in many of the older programming languages, they came up with this beautiful concept called linked list. And so basically what a linked list has is two components, right? So it has some sort of data. So I'll just try comparing it with this array sort of data structure, right? So in an array also you have some sort of data inside the data structure itself, inside one block of the data structure. But what linked lists do differently is that instead of having all these elements homogeneously arranged in like contiguous memory blocks, it does something very fun. It says, okay, the next data doesn't have to be in some contiguous memory blocks. Instead, I'll use this concept called a pointer to the next memory block, right? So I'll just form like this chain of beats. I think when most of us were young, we used to play around with these beats where we used to put strings inside them and string them together, right? So it's something similar. So you just have like some sort of data associated with each node in a linked list, and then you have this next reference pointer also that leads to the next block of data. So 5 and things like this. So on and so forth, right? And in every linked list, so in an array, it's very easy to find what would be the first element, right? So you just have to store the reference to where the first element is, and then you would be able to access all elements in the contiguous memory blocks. In single linked list, also it's very similar. All we have to do to like actually like find a linked list is just to have another variable that will point to the first element in the linked list. So this should basically be our head pointer, right? So once we have our head pointer, then we can easily find all other elements in the linked list just by uh, going to the next reference pointer in each data block. So for example, the head will point to 4. So using the this pointer to 4, I can find the other elements inside the linked list itself by just using um, the next pointer, right? So head dot next, then head dot next dot next dot next, and so on and so forth, right? So that is basically how linked lists work. And now let us look at the problem. What they're saying is, given a singly linked list with n nodes and number x, the task is to find the nodes at the given index x, one base index of linked list. So the first line of input contains a number of test cases t. For each test case, first the line of input contains space separated two integers, length of linked list, and x. Okay. So the problem itself seems quite simple to understand. So basically, they're giving us a linked list and they're saying like this is the data inside the linked list. So you just have to find the element at the position k. For example, the element at position x, right? So here they're saying the number of nodes in the linked list is 6 and the position that they want to return is 5, right? So if you look at the number at fifth position here is 1, 2, 3, 4, 5. So 657. So that will be the output. Right? So it's a very easy to understand problem. So whenever they give an index, return that element which is present at that index inside the linked list itself, right? So let's just look at how we can solve this while k is greater than 1. So just before I even code this, if well, let's just take a look at the linked list structure itself. So each linked list data block, as I said before, has two components. So that means self.data, that is what you see inside this itself. So this self.data refers to the data within the block itself. And self.next, it basically is a pointer to the next data block inside the linked list, right? Instead of calling it data blocks, I think it's more appropriate to call it a node. So a node in a linked list. So each node has two things. One is the data itself, and then the reference pointer to the next node in the linked list, right? So now, if I have to return the node at the kth position, right? And if the value of k is 1, that means I just have to return whatever data is stored in that node itself, in the head node itself, right? So what I'll do is I'll just return head dot data. Now, what happens if I have to store return the element at position 2, right? What I can basically do is I can use this next pointer to navigate through the linked list. Now, if head is equal the value of k is equal to 1, basically I just return the value inside that node itself. But if the value of k was equal to 2, so first what I have to do is I have to return the value at this node, right? I can simply do the operation head dot next once, okay, and then decrement the value of 2. So now my head will be pointing to this block. And now all I have to do is, because now k becomes 1, I just have to return head dot data. So let's just code that out as well. So while k is greater than 1, k minus equal to 1, head is equal to head dot next, right? And once I k becomes equal to 1, I just have to return that element at that particular position, right? Or the data at that particular node. Now let's just submit this. Perfect. So now this problem has been solved as well. So now let's just look at, oh, okay, this is a much more complicated problem than the one that we had before, but it's still going on the same data structure. So let's just, the next problem that we'll be doing is reverse a linked list. Okay, so the reverse a linked list, it's one of the fundamental concepts of understanding what linked lists are. And once you understand how do you actually reverse a linked list, it becomes very crucial to your whole understanding of your data structures itself, right? I feel once you understand how do you actually like manipulate these reference pointers inside a linked list, you would get much better at understanding almost any other data structure there is. Okay, so let's just quickly understand how do you reverse a linked list. Okay, so let's just okay, our problem approach always remains the same. Whenever you get a problem, read the question first. If you're not able to understand the question, then read the input and output and then the explanation. And finally, just before you even get to coding, you just look at the your exact task, what you're supposed to print out, so that you get great clarity of the overall problem, right? So basically what it's saying is, given a linked list of n nodes, the task is to reverse this list, right? So basically, in the original list, we have this linked list 1, 2, 3, 4, 5, 6, right? And they're asking us to output 6, 5, 4, 3, 2, 1. So let me just explain to you what that might mean, right? So if you look at a list like this, so this is something like the original list that they have, right? And where this points to the head, right? Now, what they basically want us to do is reverse the whole linked list. So, how do you do that? Now, you just reverse the direction of each of these pointers inside the linked list. So, this becomes this, and this becomes this, right? And finally, you make the head point to the last node. So now the whole list is reversed. So now when I access the linked list using the head, first it will start at 3, and then when I navigate through the list, so 3 dot next will give me 2, then 2 dot next will give me 1. Whereas in the original list, head pointed to 1, then when I said 1 dot next gave me 2, then when I said 2 dot next is equal to 3. So now how do I convert this linked list into this, right? So that is quite a task. So let's just look quickly how we can do that. So now, what we can actually approach this problem is, what we can do to approach the problem is introduce two more pointers, right? So I'll just call one pointer previous and one pointer called next. Okay. So basically, what the previous pointer will actually point in the uh, which the previous pointer will basically tell what is the previous node of the current node, right? So which node led to this node in the list. So for example, what is the previous node for 2? It is 1. What is the previous node for 3? It is 2. And what is the previous node for 1? It is actually none, right? It had no previous node before this. So that previous node of 1 is none. Now, then we have this next pointer. The next pointer will basically tell what is the next node inside the single linked list. So what is the next node for 1? It is 2. The next node for 2 is 3, and the next node for 3 is also none. Like how the previous node for 1 was none. The next node for the last element, the tail of the single linked list, is none. Okay. So that is the basic understanding that we need to solve this problem. So now let us look at how we can at least reverse one of these nodes. Okay. So first, or initially, the previous will be none. Okay. And okay, now let's come to this head, right? What is the next node to the node 1? So that is 2. Okay, now that we have stored 2, so basically what I tell is, first you make head point to the previous node. Okay, so remove this connection, make head point to the previous node, none. Okay, and then using this uh, next one second, I just have to clarify my thoughts here. Next is equal to, sorry about that, I just had a really bad brain fade. So our first approach would be basically into 4 steps. So the first one is that when we really have to assign the whatever the next node was there in to this node. So for example, the next node of 1 was 2, right? So first, basically, we say the next node of 1 is 2 and assign it. And then the next step would be to make this point at the previous node, right? So previous, previous, yeah. So Then what we basically do is, once we have actually made this head point to the previous node, so basically you say that uh, now before I even move to the next node, the previous of the next node will become this current node, right? So basically how that would work is, once I've assigned the previous node of the current head to the previous value, I'll change the previous value to the current node, right? So now instead of previous pointing to none, it now points to one, right? So that is how this would work. And then once I've changed the value of the previous to the current head, now how do I move to the next node? Because there was no, if I use head dot next, it's not going to go to two, but it's going to go to none, right? Because I've already changed that reference inside. I've removed the connection from head dot next equal to head dot next is equal to none, right? So now how do I change it? Very simple. That is why we stored the next reference pointer. So in order to now navigate to, I just have to use this next reference pointer. So um, head is equal to next, right? So this may have been confusing. I know for me too, it got confusing in the middle while explaining the step-by-step process, but I think when we actually code it out, it'll be much simpler for us to understand. Okay, so first what we have to do is just store a reference to the previous node, right? So previous equal to none. Now, as long as there are elements to process inside the singly linked list itself, do the following steps, right? So first, what we had to do is very simple. Just store a pointer to the next node, right? So next reference to the next node. So next is equal to head dot next. Okay. Now head dot next is equal to previous. So this is if you remember the first step, what we had to do to reverse the node was simply when you say next is equal to head dot next. So that is what we did at the start, right? So for one, we told the next node would be two. So we just stored n is equal to two. So that was the reference pointer to two. The next step that we did was we removed this connection to two and we made the connection from one to the previous node. So one to none we made. So that is what we're doing here. So head dot next is equal to pref. So we are head dot next, which was originally pointed to, we are removing that connection and making it point to previous, which is none right now. And then the third step would be, now make, before I even go to the next node, I have to set the previous of the next node to this node. So, so before I navigate to the node two, I have to make the previous one. So once I go to the previous node, once I go to two, I know, okay, the previous of two was one. Okay. Because once I go to the node two, there is no other way of knowing, coming back to the previous node in a single linked list, right? So that is the whole challenge there. So now head is equal to next. Okay. So return. Once I have processed all these nodes, uh, the algorithm will stop when I have no further nodes to process, right? So the last element the last node that was available will be the element that was at the end stored at the previous variable. So once I've done all of this, for example, just to make that logic a bit clearer, so once I come to 2, 2 will point to 1, and once I come to 3, 3 will point to 1, and finally the previous will be stored pointing to 3, but the current head will be none. So if I return the current head, right? So that will not point to 3, which is the current actual head of the list. What will point to the actual head of the reverse list is the value in the variable previous. So that is why we return the value previous, right? So let's just run this code for us to understand. Yeah, perfect. So just to go through everything again. So this process is just a four-step approach. So let me just make this new, don't save. One, two, three. Okay. So in order to reverse each of these nodes, we follow a four-step approach. First, we automatically have this previous pointer, which points to the previous node, which is actually none at the start. So first, what I do is make a reference to the next node. Okay, so next is equal to head dot next, right? So I just stored this reference into next. Now, why do I do this? Because once I make the connection between one and the previous node, there will be no other way to navigate for me to navigate a node to otherwise, right? So I have to save this arrow mark somewhere or the reference to the next node somewhere. Okay. So then what I do is head dot next is equal to prev. So what basically this does is it cuts this connection and changes it to whatever was pointing to the previous node. Okay. And once I have done this, what I have to do, I have to make the new previous as this node. So what I do is previous is equal to head, right? And finally, using this next variable that we have stored, we go to the next value. So how do I do that? So head is equal to next. So this is all that happens. And finally, when we have processed all these nodes, the the last head it will be stored in the variable previous, right? So that is the whole fundamental concept of this problem. So that was the ninth, or rather the eighth problem for today. Let's just solve two more problems and then let's call it a day, right? So one will be from in these two more problems, one both of them will be from trees, okay? And these again, trees are a very very fundamental data structure to our understanding of DSA itself. So let's just look at two concepts. One will be the traversal of the search binary search tree itself, and the second one will be the finding an element inside the binary search tree. So first, let us just go to our in-order traversal, right? So basically, what a tree data structure is basically it's like a hierarchical data structure. So if you look at trees in the real world, right? So they would have some sort of uh, trunk like this, and they'd have like some sort of twigs, and then they would have leaves and things like that. So it all progresses in some direction, right? So first you start from the root, right? And then you have some connections above it, and then these connections keep branching out, branching out, branching out, and finally it ends in the leaves, right? So even when you're talking about DSA, the concepts when we're talking about the data structure trees itself, very very analogous to what a real life tree is. So basically what a tree would have is something known as the root. So this is the base element, right? From where all the other elements inside our tree will be extracted from. So this root will have certain amount of pointers, right? So in binary trees, they are called binary because a node can have two subnodes, right? So you have one node here and one node here, and so on and so forth, right? So and these nodes can also branch out, and you can either have one child, two child, and so the node above is called a parent, and whatever nodes extend from it are called the children of that parent node, right? So and you can also think about this way: each tree is formed by various subtrees, right? So though that's also a way to think about this. And also the nodes that have no further children are basically called the leaves of the tree, right? So this root has children, this parent has children, and but these nodes at the last level, if you see this, and this, they don't have any further children. So they are called the leaves of the tree. Right, so this is basically the tree data structure. And one thing also that you can additionally notice here is in trees, right, we don't have cycles. So for example, in graph-based data structures we look at later, maybe on in the next session. So you may have these sort of cycles, right? So this node points to this node. One points to two, two points to three, and two points to three points to one, right? This is not a tree. Yeah, can you imagine the leaf of a real life tree coming back and joining to the root, or even coming back to joining the trunk, right? It doesn't happen. So it's all hierarchical. So a tree data structure is very similar. It is very hierarchical. You have a root, and then nodes are derived from that root, and then children, and so on and so forth, right? So that is basically what a tree data structure is. Now, what does traversal of any data structure simply mean is look through all the elements inside the data structure. So for a list or an array, what you would have is to, in order to traverse the array, you will assign like some sort of for loop, and then you look at each element inside the array, right? And for a single linked list, we saw a very similar traversal concept where we have this head pointer, and then using the next reference from each pointer, then like from each node, we traverse through the single linked list until we are not able to traverse anymore, right? So that is the traversal of a single linked list. Now, what are the strategies? So they're saying in this question, they're saying given a binary tree, find the in order traversal of it. Okay. So let's just now we basically have three types of traversals in trees, right? So we call them in order traversal, post order traversal, pre order traversal, and the concept is very similar. When I say very simple rather, when I say in order traversal, let's just take this example 10, 20, 30, 40, 60, 50. Okay. So, just to write a pseudo code for it, left first, left, this, and right. Okay. I mean, it's not even a pseudo code, it's just basically three keywords for us. So, when I say in order traversal, so first I say look left, take this, take this, then look right. Okay. So, what is this look left, take this, and look right? What do they mean? So, let me just look at this tree, right? I have 10, 20, 30, 40, 60, 50. Okay. So when I'm doing in order reversal, first, whenever I go to an element, if it has a left subchild, I look there. I try to explore that. Okay. Does 10 have a left child? Yeah, definitely. So I go there. Does 20 have a left child? Definitely. I go there. So now because 40 doesn't have any, now does 40 have a left child? No, it doesn't. Then what I say, take this. So what I do, basically print 40, right? And now I try looking, right? Does 40 have any right children? No, right? So then I don't have to print anything. Now, if you remember, I came to 40 from this 20. So first I try looking for a left children inside this 20 and then came to 40. So now I go back to 20. So now when I come to 20, I take this again. So 40, 20. Then I look for right children of 20. Does 20 have a right child? Definitely it does. 60, right? Now I apply the same logic to 60. Does 60 have a left subchild? No. Then I take 60, take this, print 60 here, and then I look for the right subchild of 60. Does it have? No. Now we navigate all the way back to 10. Like we go back all the way. Now I've explored all the left subchildren of 10. Now I have to take this. I have to take 10. So I print out 10. Then I start exploring all the right children. Now I come to 30. Does 30 have a left subject? Definitely it does 50. Then 50 doesn't have children, so I just take 50. Then I come to 30. I take 30, and because there is nothing else in the list, I quit, right? So this is called in order, right? In order. Now, what would post order, pre order look like? Pre order is basically take this, look left, look right. Post order would be look left, look right, and take this. So this is basically the difference between in order, pre-order, take pre-order and post-order. And just to solve one example of pre-order traversal. So again, so let's just look at what pre-order would do. First, whenever we reach a node, first we do is take this. So when I reach 10, what I do is I print out 10, right? And then I look left for 10. Does 10 have any left sub children? Definitely it does. Then I go to 20. Then what I do, the first step again pre-order, take this 20, right? Then again I look left for 20. Does 20 have any left children? Definitely it does. 40. So then I take 40. Then I look for our left and right for 40. Doesn't have. Then I come back to 20. So what I do is because already taken 20 and looked left, I just have to look right now. Then 60. Then I print out 60 and so on and so forth. So basically in order is take this, look left, look right. Pre-order is, in order is take, look left, take this and look right. Pre-order is take this, look left and look right, and post order is basically look left, look right, and take this. Now, how would you remember this? Is very simple. Always remember that look left and look right will always appear in the same order. So look left will always come before look right. So there is no situation where look left will be done after looking right. Now you just have to place the take this step in the correct position. So first, let us look at the pre-order. So you just use the keyword pre here, right? So pre means place the take this option at the first, right? In order means place the take this option between the look left and look right. So place it. So if you look here also, one comes between three and two. So one comes between the left subchannel and the right subject. So place one in between those two, or look left and look right. In post order, basically place the take this step at the end. So this is basically the whole fundamental understanding of this in order traversal. So let's just quickly code out the solution that can do this. So let we'll be storing our final result in an array. Okay, so what we basically do for in order traversal is we'll be using some sort of trick of Python which uses the extend keyword. That basically what extend keyword does is if you're trying to join basically if I have two lists like this 1 comma 2 and I'm saying extend 3 comma 4, so what this basically return me is 1 comma 3 comma 3 comma 4. Basically it just takes all these elements, separates them, and puts them back together, right? You can think of it that way. So that is one trick that we'll be using today. If root is equal to none, so if this doesn't have, if I go to a node and I find that there is no data with that node and it has no children, so will it return me any sort of logical in order traversal list? No, right? So I just have to return an empty list because if there is nothing for me to explore, then I just have to return an empty list, right? So now what is in order do? First it looks left, then it looks right. I mean, then it takes this and then looks right. So that is what I'll do. And this will be a recursive based solution, right? So ARR result dot extend self dot in order, right? Self dot in order, then root dot left. So basically, rest dot extend, you extend me the in order traversal solution of whatever is coming in my left subtree. Then what you do is you append this. So this is what this is look left step, look left, append this, right? So root dot data. Then what you do is so this will be take this step, and finally rest dot extend root dot in order root dot right. Right, so this will be our look right step. So finally, what we have to do is just return the result. So let me just run this. List has no object. Ah, yeah, it's a spelling typo. Extend. Right. So now just let me run this. Okay. So remember for both the pre-order and post-order codes or post-order traversals, the code will be the exact same. You just have to place these statements in different positions. For example, in pre-order, take this step will come before look left and look right, and in post-order, take this step will come after look left and look right. Right? So that is also done. Now let's go to the final problem for today. That will be our searching in searching for the node in the BST, right? So let's just look at that problem. Okay. So now let us find out what a binary search tree is. We looked at what a binary tree was. Binary tree basically it has two children, one left subchild and one right subchild. But why is there a concept of binary search tree? Okay. So in a binary search tree, the thing is whenever we look at a node, the node to the left of it will always have a smaller value. The node to the right of it will always have a greater value. So, for example, 2. Does 2 have any left subchildren? No, right? I then the right subchild 81 will always be greater than what 2 is, right? So 81 is much greater than 2. Now, let me look at 81. The left subchild of 81 is 42, which is lower than 81. Then the right subchild of 87 is greater than 81. The if 87 has only one subchild, that is 90, that is greater than 87, and 66 has only one subchild, that is 45, which is obviously less than 66, because 45 lies as a left subchild, right? So this is basically a binary search tree. Now, why is a binary search tree very, 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 very useful, right? So binary search tree, you can access elements in O of log n times. So what does this mean? If you looked at the first problem that we did today, right, when we had to search if there was an element inside our list, what we had to do is basically iterate through each and every single element, right? So, for example, if you had like 1,000 elements, right, inside your array, and you had to check if a certain element was present inside the element or not, I mean, inside the list or not, you would really have to sit and iterate through each of these 1,000 spaces inside the list to check if your element is present. But what does binary search tree allow us is, if you have like 1,024 elements, right? You can find the element you're looking for within 10 steps, right? And if it's 2,048, maybe in 11 steps, and so on and so forth, right? It scales to the base 2, right? So that's how effective. So instead of finding, if you have like maybe like a very very huge number, because the scaling is always like logarithmic based, it's very like the effect of scale is pretty low, right? So that is why binary search trees are very useful. They allow you to access elements in O of log n times. And now the second obvious question is, if you are able to use binary search trees, and if you're even able to use binary search algorithm for searching elements, why don't we use binary search always, right? Why don't we use binary search trees always? The reason is very simple, because whenever you're using binary search trees or binary search itself, one thing is all of these things are formed out of data structures, or it requires a lot of pre-processing on an unsorted data to make these data structures itself. For example, the most efficient sorting algorithms on very, very large data, they would take n log n time. And if you really have to even perform any sort of search on these binary search on these elements. So first you have to go through the n log n procedure and then perform binary search. Now if you remember the worst case complexity of linear search, is just O of n, right? So if you have some very, very small data that you're not frequently searching in, right? It makes no sense for you to first sort the data using a very, very expensive n log n algorithm and then performing binary search on it. Rather, you just go through the whole array linearly to find the element that you're seeking, right? So this is the difference. So when you have like this large data structure, but you're performing very, 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 very frequent search requests, then it makes a lot of sense to actually convert into a binary tree search structure, or binary search, perform binary search on it. But when you have this data structure, we're not frequently querying or searching data within it, and it's pretty small, then I feel it's best just to stick with your linear approach. So we uh, before we delve too much on that topic, let's just finish the coding of this question. So basically, okay, until when should we perform a search, right? I should perform a search until I'm able to explore more elements inside the list. For example, let me try looking for the element 100 within this binary search tree. So first I come to this element 2 is, should I look for the left subtree or the right subtree to search the element 100, right? Obviously the right, because 100 is greater than 2. There is no way I'll find the element 100 if I look at the left subtree. So then I say, okay, 2, you're smaller than me. I'm 100, you're 2. So I'll just go to the right subtree. Then 100 versus 80. 100 is again much greater than 81. So then I again look at the right subtree. 100 is greater than 87. Okay. Then I come to 90, right? 100 is again greater than 90. And when I go to the next node here, the node is basically empty. So what does empty signify? That the node that I was looking for is not present inside the search tree, right? So what I do is, until when do I continue this search operation? While there is some node for me to explore, right? If if there is no node for me to explore, I just return false. This node is not present in the array, right? So it basically says returns true if the node value x is present in the BST, else returns false. I mean, node is present in the binary search tree, right? So what are the conditions? If node dot data is equal to x, return to else node dot data greater than x greater than x. So where do I have to look? Node is equal to node dot right, else node is equal to node dot left. Let me just compile and run this code as well. If node dot data is Mhm. So the basically we have this, what is it saying? If you don't need to complete the function which returns true, the node values x present in the DSA, else return false. Okay, so again the step is very simple. While there are nodes for me to explore, while node not equal to null, uh, if node is dot data is equal to x. Okay, return true if node dot data node dot. Oh, this is a very very silly mistake from me. So if node dot data, that means if this element is actually smaller than my search value, then I have to look at it in the right subtype, right? So that just let me sum in this code. Yeah. So that is how the binary search tree algorithm even works. So basically, what you do is very simple. If there is, whenever you're searching for an element, if you're not able to search for more nodes, that means the node was element is not present in the tree. And then you basically do this comparison. First, compare the element, the key that you're searching for with the node's data. If the key is greater than the node's data, that means if I'm searching for 7 and it's greater than 2, then I explore the right subtree. Now 7 is less than 81, then I explore the left subtree. So you keep on exploring these subtrees until either you find the element or the nodes become empty. That means there is no further subtree to explore. So that is basically how binary search tree works. So today with that, we have wrapped around 10 problems from data structures. In the next session, we'll slowly move on to graph traversal algorithms and algorithms like shortest path and things like that. I also suggest you to go through these very basic strings problems and even do the pre-order, post-order traversals, and again maybe understand what single linked list traversal is for you to gain a better understanding. Thank you so much for joining this stream.